Welcome back. Now, if you have rewatched the first video on this topic, which I highly recommend before you watch the second one, because there's only two videos, so you have nothing to lose to just go back and watch the first video again, where I walked you through how to use the rules. Now, things don't always shine well and in the way you look at it. Sometimes you have to look at things differently. So I've got three different examples here. So I think I should be able to wrap this video within 10 minutes or around 10 minutes. So let me go put all the rules and then, okay, cis and trans, right? Now again, if you read the name, it already tells you you have a cis, right? 1-chloro, 2-methyl cyclohexane. Now, it's very important. It's even much more easier when you're given a name than when you're given a structure and try to find a name, okay? All right, so we're gonna do both, hopefully, okay? So draw a cyclohexane first. That's your first, point of object in doing this problem. Now, one is with chloro, so that's where you start. So 1-chloro, 2-methyl, right? So it's a 1-2, right? And what is cis? 1-2 cis is axial equatorial, right? Now, you don't want to think which one is big between chloro and methyl because there are two separate carbons. On one, you have chloro. On carbon 1, you have chlorine and hydrogen. And on carbon 2, you have methyl and hydrogen. That's how you compare between these two, right? And we know for 1-2, cis is axial equatorial or equatorial axial, So this is axial, this is equatorial, this is equatorial, this is axial, right? Now, however, between these two, if you have to determine, you will get two versions of cis. Let's draw both, okay? Let me put the chlorine here and hydrogen here, and then methyl here. Actually, you can have multiple isomers, so we don't need to draw every single one of them. Maybe on the homework, but on the test I will make it easier for you by giving only limited number of choices. So there we go. This is one cis version. Well, I would say chlorine is still bigger than methyl. So among these two, let's say, if you have to have the best of both worlds, given your circumstances on things that may not work, I would put the Cl here, right? And put the methyl here and the hydrogen here. Now, this is the best you're going to get. This is the most stable cis. Okay? There's only two real combinations. I mean, think about this, okay? I don't think you can have any other way. So this is the 2. So this is the least stable cis, because still chlorine is the biggest of this 4, and you want it to be in the equatorial position, so which is what I did here, right? So axial, I'm going to circle equatorial and axial. So the substituents are in axial equatorial, okay? Good, so this is the most stable cis. So I don't want to box or do anything. This is, as I said, this is the most stable cis conformation. Now let's look at the trans version. Again, it's a cyclohexane. So your first order of duty is to draw a cyclohexane. And then, 1-chloro, 1-2. That's what you pick. You pick the numbers and then the trans. 1-2 trans is either diaxial or di-equatorial. We know we have a chlorine and a hydrogen combination and a methyl and hydrogen combination. Both of them are big in their own pair, so you want to put them in the best possible shape. So chlorine and hydrogen, this is axial, equatorial, and the methyl would go here. This really is, or you can have methyl here and Cl. No, but you can't. Wherever you put it, this is where your numbering will start, because it clearly says 1-chloro. So wherever your Cl is, that's carbon is 1 and the other is 2. So that's very important. You pay attention to it. So this is di-equatorial. This is the most stable trans. This will be highly unstable actually, because both your big groups are in axial position. So this is probably the least stable of all of them, including the cis. So this would be Cl, H, and then methyl and hydrogen. So this is axial, equatorial, axial, equatorial. So this is diaxial, least stable. Does that make sense how I'm approaching this? Okay, so let's keep going. Again, I can sit here and whine about this whole thing over and over again, but I think eventually I have to move on so that you actually get to think about this process, okay? All right, so I'm gonna put the rules, and then let's do this one on the right side first before we do the first one. So again, 1 tertiary butyl, 3. So we know 1, 3, and trans. All you need to do is decode the numbers and then figure out the trans or cis if it's given to you. 1, 3 trans is axial equatorial or equatorial axial, right? So first order of duty is to actually draw the cyclohexane, okay? And then your tertiary butyl, which is this, basically, this is where it attaches to the ring, okay? So you attach to the ring through this. So 1, 3. Well, tertiary butyl is definitely bigger than ethyl, and this is where you attach to the ring, okay, or this side, depending on which side you want to attach to, okay? So tertiary butyl is a really big group, so you'd rather prefer that to be in the equatorial and put the axial in the ethyl group in the axial. So this is hydrogen, equatorial. This is 1, and this is 2 and 3. You usually take a clockwise route, so this will be your 3. If this was axial, this would be equatorial. So this is your ethyl, and this is your hydrogen, right? Because this was your equatorial, axial, equatorial, yeah, axial. This is your, oops. This would have been your equatorial and axial, and so we want it in the equatorial axial position, right? So this is your ethyl, this is your equatorial trans. So 1, 3 trans is, or you can have the other, which I suggested. You don't want to do because you'd rather have your hydrogen. What I'm saying here is you can draw this structure, but it's going to be really stable because tertiary butyl is such a big group. So if you're going to do that, so this is axial, equatorial, and you want your ethyl group to be here. This is your ethyl and this is your hydrogen. So this is your axial, equatorial. Make sure there's 2 carbons, and I've told you how to keep track is using dots, okay? So this is the least stable because you're putting a bulky group like, imagine you take a huge rock and put it on the edge, very edge of a branch. That's kind of what's happening here. So this, you're just putting it, let's say the branch is actually on the ground, you're putting the rock on top, it will make no difference. So this is more stable of the 2. Even though we know in 1, 3, cis is more stable. All right, now let's come back to this structure here. Again, I'm asking you to put them in right places. I didn't say, like I said, when you have 3 substituents, okay, here we have a tertiary butyl 1, here we have an ethyl, and we have a hydroxy, right? So you don't really have to go by the rule because this is really only for one This di substituted, this is tri substituted. So this is easier in a way, but the figure itself might look a little scary for some of you. So all you've got to do is first draw a cyclohexane. You know, if you look at the priority sheet, this will be 1. And again, which side you go 2 or 3 really doesn't matter because it's only attached through a carbon 1. So I'm just going to go 1, 2, 3, 4, 5, 6. Not that we will use these numbers, but I'm just saying the numbering here has really no real meaning. So I'm going to start here. In this carbon, you have a hydrogen and a OH. So hydrogen is the smallest of the two. Put that in the axial position. Put the OH in the equatorial position. Okay. Now, people, you can start from here too. This could be 1. This could be 1. I can show you another version of it. So just so you know. And then your 3 is ethyl. Well, this is your equatorial. This is your axial. So you want your ethyl to be in equatorial and your hydrogen to be, because that's the biggest of the two, right? And then you have 5, which is here. Again, this is equatorial. This is axial. So this is where I would probably have my tertiary butyl, okay? So this is my hydrogen. Simple. All you got to do is do it this way. Now, there's no, when you have cyclohexane, every carbon could be 1. So, you know, instead of it being starting from here, if you start from here, well, the position is still the same. You can call this 1, 2, 3, 4, 5, 6. In this case, this still retain this way format, so it makes life so much simple. Okay, so this must have been axial. This is equatorial. If this was your 1, your OH goes here, and then 3 would be this, and again, ethyl would be here, right? And then your tertiary butyl would be over here. The sol hydrogen, right? See, it really doesn't matter where you start the 1, but you got to be consistent. Don't change 1 and also change this. Keep this the same, okay? Keep these the same. Okay, don't change these around. It's going to be very difficult if you do this, all right? All right, we got one more and we can call this a wrap. Okay. I want you to draw, you know, let's see. Okay, let's say you hanker one, okay? Usually this is called the hankering process. Let's say I want you to actually use open and closed wedges to appropriately convert the structure with this form to this form. So here's what I do. My OH is my high priority group, so I give that 1, okay? And I guess you can call this, you know, the number, see, this has to be 1, and then from there, it doesn't matter which way really you go, okay? All right, so here, this is equatorial, right? This is axial. This is hydrogen, and this is equatorial. This is axial, right? And then this is equatorial, this is axial, right? This is what I meant by, like, you have to also remember that this is cis with respect to 2 groups, and then this and this combination is trans, right? Okay, let's keep this. So I'm hankering the OH, so 1, 2 is, this is the big of the 2, so I'm going to call this 1, and this is big of the 2, so this is 1. The 2 big groups are in axial equatorial, right? So with respect to OH, The axial equatorial 1, 2 is cis, right? So let's go draw the cyclohexane again. So with respect to OH, CH3 is cis, right? So it really depends on what you start here. If you start this, then this has to be your methyl, okay? That's all. It's very important. If you start with this, then this has to be also open bench. And then one, this is the big of the two. So this is 1, this is 2. So 1 and 1 are in diequatorial, so that's trans. So with respect to Cl, OH is trans. So here, Cl is trans, so the hydrogen is this. We don't need to show that, but what I'm saying here is, let's say you're debating, you know, some people always want the other, okay? They just think that way. So say if you started with this, then with respect to OH, CH3 is cis, so this has to be this, and the Cl is trans, so it has to be this. Keep in mind, the 1,4, 1,2 business is slightly different than, you know, so I'm just leaving this as a benchmark. So if you have to convert this, I will tell you to convert it. Again, you got to remember this, you got to remember the rule, and then know how to put it in place. So don't always assume cis means this, trans means this, okay? You also have to incorporate the rules, because we're doing hankering. We're comparing one and one, one and the other, okay? So that's all I really want to say more on the topic of cyclohexane. I'm sure we will do some problems, and you know, we got other areas to cover. So I want to wrap this over here, and then I highly recommend you watch both videos at least more than once if you haven't got it the first time. All right, even if you did, just watch it just for the kick of it. All right, so stay tuned for videos on other topics.